I have a question. Because I'm not a scientist, I'm not even sure if I'm phrasing this right.
Okay.
In regards to dark matter and dark energy, and earlier you were you made a passing reference to string theory and higher dimensional states. Is it at all possible that if there is more than 3 physical dimensions, that something is existing in higher dimensions that has a gravitational effect on our universe?
These are all some of the ideas that are being explored. At present, we don't have the experimental precision to do it. I mean, the nice thing about dark matter, saying it's a subatomic particle, is it's kind of the simple one. We've got particles, we have the quarks, which feel the gravitational, the strong, the nuclear, and electromagnetic forces. We've got the leptons, which are like electrons, which feel the electromagnetic and the weak and the gravitational force. And then we've got the neutrinos, which feel the gravitational and the weak force. And it seems like maybe there should be one more particle that just feels the gravitational force. That's my excuse for it. Is there's this strange symmetry in terms of the particles that we know that it seems like, well, there's might be something missing down there. So I favor that particular explanation. But yeah, right now, that's why there's so many people working on it, because potentially there's a Nobel Prize in there for the person who figures it out. But I think we're still kind of a lot of years away on some of this stuff. Yeah, yeah.
I hope this is a hilariously ignorant question. I'll entertain some people, but we've estimated something about the rate at which the universe we know of is expanding based on the shift.
Mm-hmm, the redshift. Right, right.
And we went back to their space, to their speed going away from us. If all this dark matter is somehow in there, is there some way it could also be tampering with the shift?
Well, it's doing it through its gravitational influence is the way it's usually done. It's altering. The expansion is changing based on the gravitational force of all these objects inside this region, including the dark matter. And so that's probably the simplest explanation. I mean, the value of the redshift is, we measure that kind of directly, but it's only individually, but it's only kind of in looking at them in bulk in all these objects that we can try to get a better sense of what's making stuff move. But yeah, the dark matter is definitely influencing that to some extent, because we have to include it in the cosmological equation. When we want to fit a model to match some of the big surveys and stuff like that, it turns out that you get the best fit for your redshift relationship and other things that we measure in terms of how galaxies are distributed. We get the best fit when we include some dark matter in there. So it's definitely an influence, but it's one of these things that's sort of the background. It's
Yeah, I think that's the best
There's no
answer.
theory yet on how a lot of dark matter could itself somewhat enter into the amount of the shift to a degree.
Well, that's how it would. I mean, the one number that we can measure effectively is one of the numbers we can measure effectively is the redshift. But that's it's sort of like the speed of a boat moving through water. Well, okay, you can measure the speed of the water, and that'll tell you about you can measure that speed, but you don't know how much of it is the boat applying engines versus how much the water is carrying it. Well, suppose you have, instead of water, it's something more viscous, where the boat has to apply more power to make it move. There's effects like that the dark matter is kind of the background material that it's got to move through, and that's going to influence that just through the gravitational influence alone, and so we have to. The best models fit when we include something like dark matter to match it up. But again, it's not something that you can that they do with one galaxy. You sort of have to consider all the galaxies. That's why they're doing these big surveys like Sloan and stuff like that, is they get a distribution of galaxies, and that tells us a lot more about how they seem to be distributed, and that influences a lot, because there could be clumpings of dark matter. We have good reason to believe that dark matter clumps at some level. And so that influences things. I mean, something could be on the other side of something that's a lot of dark matter and would influence the spectrum maybe in different ways. Right now, it's all a lot of areas of research, and so there is no set answer as yet. But again, Newton's theory of gravity, they didn't prove it wasn't crystal spheres until they sent something to another planet. Yeah.
Just one question.
Sure.
I don't understand these iPods and cell phones and all. Is there anything in that started out from astronomy specifically?
Well, a lot of the quantum mechanics development, and this is kind of my point in the second part, and actually I go into it even more when you get into the nuclear physics part. A lot of the quantum mechanics, there were some experiments that they could not readily do initially on Earth. In the case of the nebular lines, they saw these spectral lines, but they couldn't see them on Earth. They found that there were these metastable states that were in atoms that they found experimentally, and they used the quantum mechanics to figure out, one, where these states had to be, and two, how would they do the transitions, and were able to use that to design an experiment where they could see the spectral lines, these forbidden lines, on Earth. And in fact, the term forbidden line is kind of an archaic term because they saw these things in these energy states, and they didn't see them emit spectral lines, and so they called them forbidden lines. They didn't know why they were, quote, forbidden, but it turned out it wasn't forbidden, it was just that they were like extremely unlikely. They weren't absolute forbidden in an absolute sense. They were just, just their previous experiments did not reveal under what conditions they would emit. So astronomy helped provide that guide on there. And the quantum mechanics is, again, integral to the development of semiconductor electronics. One of the guys that I was digging around, one of the researchers who did some of the first studies of the impact of quantum mechanics in terms of energy sources in the stars, trying to figure out how the stars were powered by nuclear reactions, he would, later in that year after he published this paper, he would write the two important papers that founded semiconductor electronics as a science. Prior to that, they had these things they called semiconductors, and they used them as crystal. They were the crystal in the crystal radio sets, the crystal diodes. They worked. They didn't know why they worked. And this guy named Alan Harries Wilson wrote the paper that sort of defined what there was with energy levels and the way atoms behave whenever they are in bulk. We always see the simple model of the atom in classes where there's the energy levels of the quantum orbits. But when they get mushed together in matter, these energy levels start overlapping in ways, and they create the conduction bands and the insulation bands and valence bands and stuff like that. And that is important in semiconductors. That tells you where these atoms are going to be, how their conductivity properties are going to behave. So yeah, it's really kind of roundabout, but that's one of the cool things about physics and why James Randi called physics the queen of the sciences. Fundamentally, if you know all the science and assemble it correctly together, you can predict things mathematically before you actually do the experiment. And that provides extra, oomph to the believability of your experiment and your theoretical interpretation of it.
Thank you again.